Okay, so welcome to our training today. Today, we want to look at the concept of bit commitment. So, in bit commitment, with what we have Alice and Bob who are exchanging information, but then there are trust issues. So, what Alice does is to flip a coin, and in flipping that coin, we will consider that supposing that he chooses the head, that will be 0, and then if he chooses the tail, that is 1. And we make a choice for Alice, so Alice chooses the tail, which is 1. Similarly, Bob could have also chosen this side of the coin, which could be 1 or 0. And we are going to use this link, random.org, to generate a 32-bit random number. So we go over here, we input the bits that we wanted. With 32 bits, it's basically 4 bytes, so we choose binary, and then we can get the bytes that we are looking for. And here we are with the random number that we generated, which is 32 bits. But then, according to the question, we need only 31, and then we will change the last bit to reflect the choice of Alice, which could be for the head. Alice will choose it as 0, and then also if you are choosing the tail end, it would have been 1. And we will use nano to create the file in Replit, and then we will hash it. So with nano, we have already created that. So if we do that with Alice choice, so Alice have chosen that, and then we paste it, right, copy and then paste, and we check, and that is the information. So that means Alice have made a decision of choosing the tail. Once Alice has made a decision of choosing the tail, she doesn't need to disclose it to Bob, but what he has to do is to compute the hash of this message and then share that with Bob. So to compute the hash of that message, we'll run this command, open SSL digest with the file, and once we do that, the messages gets hashed, and we have the SHA-512 message hash here, which gives us 512 bits of information, and this is the information that he's going to share with Bob. So once Bob receives the hash, Alice then could not deny what information that he's sharing with Bob right now, because he already shared a hash with it. And generally with bit commitments, it also requires Bob to prove his trust to Alice in a mutual way by also sharing his side of the bit commitment. So Bob's choice, you could have hashed it. So then after the commitment, we go into the verification stage. And in the verification stage, Alice will now share the true information that she wanted to pass across, and Bob will take that information and then compute a message digest, a hash function for that message, and then once he gets the results of that hash, he will then compare that with what he had previously received from Alice. So let us suppose that that is the message that Alice now shares the true message with Bob, and there we are, copy paste, and Bob takes this information, and then Bob also computes the message digest for this result. So message digest is here. Okay, so Bob gets a share of the results that Alice is sharing, and then what it does is to do a comparison of the two. So if Bob compares the hash with the previous hash that Alice shared, and both are the same, then Bob accepts the results of the coin toss and says that what Alice has shared is truth. Otherwise, Bob rejects it and considers Alice's information as falsified. That means Alice falsified the results. So to do that, we pick the first hash and then pick the second hash, and then we do a simple comparison using Python script. So have it, and then we just paste it here, and there we are. It tells us that the hash are equal, therefore Alice is speaking truth. Okay, so thank you for being here. So we just explained bit commitment with this practical example. Thank you.